Sony Interactive Entertainment operates under a punishing dual mandate. They must deliver pristine, zero-latency local rendering for consoles and VR, while simultaneously scaling a massive global digital infrastructure to support over 100 million players. But stretching standard internet and rendering architectures over vast physical distances forces this infrastructure to its breaking point. When streaming cloud gaming, standard internet routing protocols inevitably trigger microbursts and drop data packets. This creates input lag, a physical delay between pressing a button and seeing the action, which instantly renders competitive gaming unplayable. Concurrently, rendering massive, persistent online worlds requires calculating the state of continuous geometric ordinate grids. Relying on classical game engines to process those continuous spaces demands a server capacity that is financially impossible to maintain at scale. Sony cannot overcome these bottlenecks by simply brute forcing more server hardware. Escaping this curse of dimensionality requires a departure from classical computation. A recent postdoctoral analysis evaluates a mathematical alternative designed to solve these exact scaling limits. It centers on two frameworks developed by Tensor-Networks Incorporated, the Predictive Tensor Control Plane, or PTCP, and Tensor-Network Quantum Gravity, or TNQG. This postdoctoral evaluation outlines the strategic integration of tensor-native mathematics into the core infrastructure of the PlayStation Network and PlayStation Studios. This matrix details the physical limitations hindering PlayStation: cloud lag, telemetry overload, rendering costs, and security vulnerabilities. The right column proposes an alternate reality. Cloud streaming matches local hardware, and environments consume near-zero compute. This requires replacing continuous spatial mathematics with discrete tensor networks. This matrix serves as an operational roadmap. By solving the underlying math problem, Sony can convert rigid hardware limitations into highly profitable, dominant positions in interactive entertainment. The primary barrier to cloud gaming is tail latency input lag. Standard network routing operates reactively, sending data down paths that are already becoming congested. By blindly dropping packets into a central bottleneck, the network forces the system to stall and completely wait for retransmission. The Predictive Tensor Control Plane provides an orchestration layer built to ignore standard internet congestion mechanics. Instead of reacting to collisions, PTCP uses a risk metric called conditional value at risk, or CVAR, to predict where congestion horizons form, calculating an optimized geodesic routing path in advance. Interactive video frames and controller inputs smoothly bypass the cluster before the bottleneck even materializes. By predicting and routing around town latency stragglers, the network guarantees an artifact-free stream. The delay is eliminated, making a remote server feel exactly like local hardware. Perfecting the stream solves only part of the infrastructure problem. The PlayStation Network must process the hyperdimensional telemetry of over 100 million concurrent active users. During peak holiday traffic, the sheer volume of concurrent state data overloads authentication servers and matchmaking control planes, triggering massive outages. PTCP directly addresses this memory limit by taking that multidimensional data and systematically collapsing it down. This algorithm outputs a pattern-of-life tensor train, compressing the telemetry into a strictly bounded memory estimation denoted as O of dnr squared. By mathematically capping required memory space, the network absorbs exascale holiday loads without expanding physical hardware. The infrastructure remains stable regardless of how many users log in. Beyond the network layer, PlayStation Studios faces the crushing computational economics of spatial rendering for live service multiplayer games and PlayStation VR 2. Traditional game engines operate on continuous mathematical grids. They calculate physical states and render environments uniformly, consuming massive amounts of server and GPU energy, even if a virtual sector is completely empty of players. Tensor-Network Quantum Gravity, or TNQG, eliminates this rigid grid system. TNQG operates as an operational reconstruction program. Within this framework, spatial distance is calculated purely as an inverse function of player and object interaction capacity, also known as entanglement. When players congregate in a specific sector, their entanglement spikes. The engine probabilistically renders high-fidelity physical geometry strictly where those interactions occur. If players leave or are not interacting, the engine mathematically coarse-grains the environment, dropping the rendering compute back down to near zero. Discarding continuous grids in favor of emergent geometry, drastically reduces the thermal load on local hardware and the server footprint of live service games. It provides an affordable architecture to construct infinite-scale planetary virtual worlds. Operating at planetary scale also exposes gaming networks to massive volumetric distributed denial-of-service attacks and sophisticated data breaches. Classical network security relies on deep packet inspection to scan semantic heuristics, but reading individual data payloads introduces heavy latency, degrading the performance of real-time multiplayer lobbies. PTCP replaces deep packet inspection with the D-Topo defect score. This is a topology-native alternative that completely ignores the payload, treating global network security purely as a discrete geometric anomaly. If a compromised node attempts lateral movement or a botnet initiates a volumetric attack, the malicious traffic physically deforms the mathematical curvature of the network. The D-Topo score instantly calculates this change in graph curvature, flagging the physical anomaly exactly where the traffic flow is being warped. Once flagged, the system triggers an automated safe policy envelope. It quarantines the deformed sector, while normal data flows uninterrupted. This payload-blind quarantine forms an impenetrable perimeter. It protects user data and ensures 99.999% network uptime, without adding a single millisecond of inspection latency to multiplayer games. Returning to the business benefit matrix, the raw mathematical functions of these frameworks translate directly into objective business outcomes. By perfecting cloud streaming with predictive routing, Sony immediately expands the total addressable market for PlayStation Plus Premium, acquiring players without a physical console. By utilizing emergent geometry, the exponential server costs of rendering massive live service titles collapse to a fraction of the standard compute burn rate. PTCP and TNQG function as the foundational financial architecture required to make infinite-scale interactive entertainment sustainable. This creates a stark division in the industry. While competitors continue attempting to force classical computing hardware past its physical limits, PlayStation is sidestepping the physics problem altogether. Relying on reactive IP routing and continuous spatial game engines guarantees high latency and unsustainable overhead. Achieving unparalleled interactive scale requires abandoning continuous mathematics entirely, rather than merely optimizing older internet mechanics. By anchoring its core infrastructure in discrete tensor networks, Sony acquires the mathematical framework necessary to secure its network, maximize its gaming revenue, and completely dominate the next generation of spatial computing.